the gathering. Thank you, madam. Good afternoon, everyone. It's my privilege to introduce our guest speaker of today's program, Professor G. Adikavi Nannaya garu. Sir is a renowned scientist with post-graduation from Andhra University and Doctor of Philosophy from University of Delhi. With over 32 years of experience at CSR National Physical Laboratory, New Delhi, he superannuated from NPL as Chief Scientist, Professor and Head Crystal Growth and X-ray Analysis Activity. Later, he served as Professor at IIIT Noojveed and KL University and also served as Director for IIIT RK Valley, Andhra Pradesh. Currently, he is working as Dean Research Honorary at VSM Group of Institutions, Ramachandrapuram. His research focuses on non-linear optical and high-energy detector bulk single crystals and their characterization by various high-resolution X-ray diffraction and scattering techniques. Sir has published over 300 research articles in reputed journals with high impact factor and also published 60 papers in proceedings with over 9,300 citations. He has the prestigious international recognition like by the recent survey of Stanford University, Nannaya garu is in the top 2% of Indian researchers. He received many awards like Material Research Society of India Best Paper Award and Professor P. Ramaswamy National Award for Crystal Growth and many more. He holds a patent and has been granted for the development of a new non-thermal annealing technique for the fabrication of shallow PN junctions. He collaborated with many R&D and academic institutions like Delhi University, Annamalai University, WIT University, etc. and delivered more than 170 invited lectures, chief guest addresses at different conferences and institutions in India and abroad. With this brief introduction, I welcome our distinguished guest, Professor G. Adikavi Nannaya garu, to deliver his presentation. Thank you.
Good afternoon to one and all. At the outset, I would like to say thanks to the Honorable Vice Chancellor for giving me this opportunity. At this now actually today is a culmination of 3 auspicious events. One is birthday of this university, that is the 18th Foundation Day, and the birthday of our head of this institute, that is Vice Chancellor sir. And third is, of course, this is about the program by the national program actually. So this developed India mission 1947 to 2047. So I am very happy to grace this occasion and at this. Okay. So the title of my talk is Research Methodology through Illustrative Examples of Advanced R&D. Equality, education and research are essential to face the highly competitive world for any country's economic growth, energy and health securities and environment protection. The present talk is designed in such a way that it should inspire and orient the young faculty and students towards the innovative and advanced research. What this is from this? Okay. So this is of course the outline. It is a big talk actually to cover the audience who are having different disciplines. It is a bit lengthy talk, so you have to bear with me for quite some time. So next slide please. So the first is actually I wanted to give a brief introduction to national standards and National Metrology Institute of India. Why it is necessary? Standards ensure the safety, quality and reliability of products and services. They facilitate trade and protect our health and the health of environment. For global trade and economic growth, every country must maintain standards with accuracies of international acceptance. Next slide please. Okay. So NPL is one of the premier and earliest institutes of CSR. It is formed on the 4th January. The foundation stone was laid down on 4th January by late Pandit Jawaharlal Nehru. That is before independence. And the main building of this lab was formally opened by Sardar Vallabhbhai Patel on 21st January 1950, and CSR was established on 26 September 1942, and CSR Foundation Day is celebrated every year on 26 September. NPL is open to all citizens of India, including school children on this day. Next slide please. Okay, this is the front view of the main building of the NPL. Next slide. So it is the apex body of national standards, that is National Metrology Institute of India. Recently, a revision of SI units took place based on a redefinition of the kilogram, meter, ampere, Kelvin and mole in terms of well-defined and precisely measured basic constants like H, that is a Planck constant, C, velocity of light, E, charge of the electron, K, Boltzmann constant, and Na is the Avogadro number. And actually, earlier we used to use these old standards of meter and kilogram, which were based on the platinum rod and platinum iridium alloy cylinder kept in BAPM Paris. For every 5 years, we used to take our standard, prototype standards, and go to Paris, and we had to check. Now there is no such necessity. It is redefined with well precisely measured basic constant H, C, E, K, and Na. So next slide, please. So I will not go into much details about NPL, but a few things I have to tell. The main mandate of NPL is to establish, maintain and improve national standards of measurements and to realize the 7 SI base units, meter, kilogram, second, Kelvin, ampere, candela, mole and 2 supplementary units, radian and steradian. it is the only one laboratory which is written in the Constitution for its mandate with this under this Weights and Measures Act 1956 and 1976. And besides this, we have a materials development and characterization activities. In this novel materials like metals and alloys which are used in the satellites, and advanced carbon products like carbon fibers, polymeric and soft materials, liquid crystals, single crystals, whatnot. There are so many novel materials that have been developing here. And similarly, we have a sophisticated characterization facilities like powder XRD, XRF, HRXRD, SEM, TEM and so on, name anything, they are available. And these are not only used for the in-house projects, but also can be extended their services to the other institutions and also the defense research laboratories. So the third one is a global change research, that is radio and atmospheric sciences. Under this global change research, estimation of greenhouse and other toxic gases, and then Antarctica environment studies also there. So as a team leader from NPR, we have 3 stations, Dakshin Gangotri, Maitri and Bharati. So these are the main activities of NPR. Next slide please. Okay, actually to maintain the standards, its precision, accuracy is the utmost important. It should be acceptable to the international community. For example, as a typical example, I am showing this time standard, that is the CSIR NPS, one of the world's most accurate cesium fountain clock. Its accuracy is 10 to the power of -2 per day. So in a normal words, it is equivalent to say that the clock may lose or gain only 1 second in a span of 40,000 of years. So that is the accuracy limit, and it works on the high performance transition of cesium 133. It is the 1 second is defined as 9 billion 192 million 631,770 periods of this 130 hyperfine transition between f is equal to 3 and f is equal to 4. This is the transition that we are using, and these many times is equivalent to the 1 second. And this is a block diagram of this time clock, that is a microwave solid state oscillator generates frequency for this clock, and this is compared to the atomic reference. If there is any deviation, it will go as a feedback signal and it will be corrected. The Honorable Prime Minister of India, in his virtual address at on December 4, 2020, dedicated to the National Atomic Time Scale on 26 February 2021. The Honorable President of India, in address, mentioned that as one of the milestones of India's achievements. Next slide, please. Okay. Actually, in the research methodology, I have taken some of the basic concepts and the slides from our colleagues at NPL, so I should acknowledge them. Next slide, please. This is a survey by the very prestigious journal Nature. The number of PhDs per year produced by various countries is given here. Though we are we have the population equivalent to this China, but we are at very low. This thing, we are at the 4th place. So to match the explosive growth of economy and population, we should have much more PhDs. Let us hope that in the future there will be more. percentage per capita also, India is at the 4th stage. As per the population, it should be at the first actually. Next slide, please. Let us see quickly this classification and conducting steps of research. So, before going to the definition, first let us or productive search. It is nothing but research is simply the cyclic search for truth in a potentially infinite number of disciplines or topic areas. That means you can choose any topic. There are variety of disciplines of science and arts. You can take anything. You can do the PhD in infinite number of disciplines. And the process by which knowledge is acquired, that is another meaning of this. And creative work undertaken systematically to increase the stock of knowledge and the use of this knowledge to devise new applications. And the definition, research, it is defined by many researchers in different ways. A few of them are given here. In the broadest sense of the word, the definition of research includes any gathering of data and facts for the it is a process of to increase our understanding of a topic or issue. It consists of 3 steps: pose a question, collect data, answer the question, and present answer. So like that you can have different definitions. These are the important definitions that I have mentioned. And of course, there are 7 ways of classification of this research. So here, original research. To produce new knowledge rather than to present the existing knowledge in a new form. And basic research, second one, understanding of fundamental principles. And third is applied research, finding a solution for by society. So that is very important actually. We need energy, healthcare and all. We have to take care of those things. And primary research to collect original primary research data. And secondary research is analyzing of existing data of research. And qualitative research, exploratory research to understand the behavior. For example, inelastic scattering of light, first noticed by Sir C.V. Raman, and quantitative research to establish a research hypothesis that is example is Raman scattering or Raman effect. Next slide, please. Okay. The various steps in conducting the research are as follows. And the first is identification of a research problem, then literature survey to note to start. We have to start from where that is decided by the literature, that is the present knowledge. Specifying the purpose of research, we have to know, actually we have to specify what is our motive, what is the purpose of research, or determine or resolve specific research questions or hypothesis and data collection simply by gathering or by experimentation and analyzing and interpreting the data and reporting and evaluating research. Next slide, please. Okay, we should have, to do research, we have to have creativity and thinking and creative thinking as well. So with illustrative examples, I will explain these things. Next slide, please. Okay, so actually we have to check ourselves how simple or complicated our thinking in analyzing a situation. So there are 4 simple questions here. How do you put a giraffe into a fridge? How do you put an elephant into the fridge? The king of the jungle is holding a meeting for all of the animals. One of them is not there. Which one? You are standing on the bank of an alligator infected river and have to get to the other side. You have to cross the river. What you do? Actually, 90% of the managerial staff, they answered incorrectly, and also sometimes they could not answer even. But the school children, they answered very well, because we are biased with our thinking. First we will think that, oh, this much fridge, where it is available, how to take it to the forest. Like that, there are so many biased thinking from a managerial type. But the school children will not think. They will straight away say, open the fridge and put it in the giraffe and close it. The elephant into the fridge, out this and put the element in the fridge. And the king of Bengal is already holding a meeting. So which one is not there? Naturally, the elephant is inside the fridge, so it will not go there. And already all the animals are attending that meeting, so you can easily cross the river by simple swimming. Next slide, please. Next. Okay, here is a picture. So which contains as such, it is a randomly black and white picture. But if you concentrate on these 4 spots, so and by changing our perception, you can notice that it is a saint's face with a beard here. So like that, it depends upon how you are actually concentrating your thinking and your perception. Next slide, please. So this is the art actually on a wine bottle. Immediately one can say a couple in an intimate pose, but the children readily tell, they will see there are 9 dolphins in this art. So like that, it depends upon the biasing. Unbiased perception is very important for research. Next slide, please. Okay, sometimes, so a complicated issue may be solved by making it pieces or parts. Here, one prominent face you are seeing, but it contains so many other faces also. Here, one person is there. Here, there are 2 faces, and here also one face. And here, if you see clearly, one here on the top, another, and here one is front side, and one is at this side. So you have 9 faces actually. So you have to think unbiasedly. Then, if there is a complicated thing, you can make it in parts, and you can really analyze in a simpler way. You can get the solution easily. Next slide, please. So this is a picture, basically coffee beans, and here there is a hidden man's face. Can anybody tell where it is? Is it there? Anybody can raise your hand if you see? I think there is somebody, okay, raise their hand. That means actually it is how quickly we can identify the hidden item. Here it is there. So that is also one quality to do a good research. These things we have to inculcate ourselves in our knowledge. So that is the thing. Next slide, please. So now we will go to this objectives of R&D and their explanation. So next slide, please. Okay. So actually to observe or verify and test or define, postulate important facts. So around us there are so many things or events that are there. We have to observe properly, like the sky looks blue in the daytime and red during sunrise or sunset time, and like a dispersion, our sunlight contains 7 colors, and so on. Rayleigh scattering, Mie scattering, and Compton scattering, so on. How the rainbow form, what is primary rainbow and what is secondary rainbow. Like that, you can see so many things in the nature. You have to understand, you have to first observe, understand, and then postulate what is the reason behind it. So like that you can habituate yourself, your thinking. Next slide, please. So this is, for example, to analyze an event or process or phenomena to identify the cause and effect. So this is a greenhouse effect which is causing global warming. This is a very burning topic actually. How it is happening actually? You see, we have a lot of greenhouse gases and pollutants like CO2, NO2, NH3 and so on. So these are actually, while the transmitting this sun rays through the atmosphere, it will go straight away and it heats up the earth. But in return, earth gives back only the infrared radiation, but it will reflect back with these pollutants. So that is why the earth is getting warmer and warmer. So we have to stop producing these greenhouse gases or pollutants to safeguard our earth. Next slide, please. Okay, this is sometimes while doing our experiment, some unexpected results may be observed. So that you have to be very keen and observe. Don't ignore that. Sometimes these type of things will give a invention or a discovery you may get. This is, for example, ion implantation of various dopants. You know that ion implantation is the best method to implant the dopants at a predetermined depth. This is one of the best techniques of doping in the VLSI and the ULSI technology. So, but the thing is, actually, while doing so, your surface will damage a little bit. So you have to recrystallize. There are some methods like thermal annealing, rapid thermal annealing, laser annealing and so on. But all these are having the temperature effect. So there is a thermal diffusion of dopants because of thermal nature. So actually while doing the experiment, okay, these are the diffraction curves. This is for a blank wafer and these are recorded at different doses. As the dose go on, the quality or the crystallinity is deteriorating. So this half is increasing, half is will tell the same thing. So we have to, actually while doing the experiment, I found that this curve is never altering, but these are getting sharper and sharper with time. So then I thought there is something that is going on, annealing at the room temperature itself. Then with a microwave frequencies electromagnetic waves, at a certain timings, I have exposed these crystals, and then again we have taken this the diffraction curve. For example, here this is 6.5 curve of the black wafer, and this is immediately after taking the it's half it increase, means there is a crystal disorder. So to anneal with this annealing method, and then it is almost coincident with the wafer. So there is no temperature involved. Without the diffusion of dopant, we can make very shallow junction for VLSI applications. So this slide to a next slide, a patent. Next slide, please. Okay, so not only we should have a very precise instrument to really see such minute defects. So I have already developed this multi-crystal X-ray diffractometer at NPL after I joined. It is a state-of-the-art, world-class diffractometer. So this is very sensitive to such changes. Next slide, please. So we can go up to the theoretical limits, close to the theoretical limits. So then only really we can see such small differences or the small disorders. So this is also very important to do a good research. We should develop good tools tools. That is my main emphasis of this. Okay, next slide please. This is a photograph of this instrument, and this is one of the papers, among the top 70 papers published by CSR labs, that is 37 labs, in 70 years, that is 80,000 papers. Out of 80,000, they selected 70. This is one among that. Next slide, please. Okay, to develop new scientific tools, concepts and theories to solve and understand scientific and non-scientific problems. So Raman effect and FT Raman spectrometer is typical examples. Next slide, please. Okay, so you see, in a molecule, at all finite temperatures, the atoms are not stable. They will vibrate around a average position. So with a particular very specific energy, if you find out that energy or measure that energy, you can identify that molecule. It is a fingerprint. If you know that change of the that intensity that is coming through the rotational rotations of the atoms, it is a fingerprint of the molecule or a functional group and so on. So here you see, because of that specific energies in the spectrum, you will observe some bands which lies in the infrared region. Actually, when it is already in the excited state, like a stretched spring, its additional energy will be given to the incident radiation, and hence the scattered ray will have more energy or higher frequency. That we call it as anti-Stokes Raman scattering. And when it is at a ground level, then it will receive some energy. So therefore, in the scattered intensity, it will lose some energy. That is called Stokes line. So this is observed by Sir C.V. Raman and invented this Raman scattering or Raman effect. So the change in this frequency is known as the Raman shift, that is defined by this equation, that Raman frequency shift is 1 by lambda incident minus 1 by lambda scattered. You can measure this by this Raman spectrometer. Here with the NDR laser, the laser is focused on the sample, and the scattered radiation is collected by a parabolic mirror, and the parallel beams will enter into the Michelson interferometer. And here, in the presence of this beam splitter, 50% will go towards this mobile mirror and 50% will reflect towards the fixed mirror. In 1 second, this mobile mirror will move 1 centimeter. Within this 1 second and within this movement of 1 centimeter, the detector measures or record 1000 points. Okay, so this is fed to the computer by this FT Raman, this Fourier transformation. Fourier transformation, you can get the Raman spectrum. Okay, we have to do 2 times. One is with sample and without sample. If the latter is subtracted from the former one, you will get a Raman spectrum. Next slide, please. Okay, this is the Raman spectrum recorded for a urea-doped zinc thiourea sulfate. Actually, in this urea and thiourea, the atoms are same. So therefore, no elemental instrument, analysis instrument will give any indication that whether these are urea is doped in the crystal or not. So the only thing is by the FT Raman or FT air also okay. So here you see the only difference is there is a here in the urea COO bond is there, and in thiourea CO bond. So they have a different spectrum, absorption spectrum. You can see with increasing the molar concentration, there is enhancement or prominence in the absorption spectrum. So likewise, you can find out, you can quantify also these the urea concentration. And we have grown at MPL variety of technologically important crystals, and this is for high energy detection like your MRI scanners. This is a table salt basically. When you prepare it in a single crystal form, it is used as a infrared detector, which is used in the war field in the night times. And these are the nonlinear optical crystal, KDP and lithium niobate, etc. These are used in your nonlinear optical applications, including second harmonic generation. Now these same crystals can be used for generating for the quantum computing also. There you have to have this entangled photon pair. So from this, with the down conversion of photon, you can get this entangled photon that I will say a little later. So like that we have grown variety of crystals at NPF which are technologically important. Okay, next slide please. Okay, this is a application in the semiconductor industry. So here, these are the silicon germanium layers grown on a SI substrate, which are needed for the high frequency communication. Here, up to some thickness, it is exactly lattice match, that is A panel is equal to A substrate. But during the device fabrication processes, that is annealing, there is a Raman shift. You can see from this place to slightly it is deviating. The shift is there, and similarly with the X-ray diffraction also, we can see that the film peak is shifted towards the substrate peak. So that next slide please. Next slide. Okay, there are two equations, and both are function of X, that is germanium concentration and relaxation. So by solving these two equations, you can get these two important parameters which are needed to decide whether this device is suitable for the industrial application or not. Next slide please. So to avoid very lengthy calculations, we have given a graphical method with this actually from Raman shift and a lattice constant from XRD. You can just put this to point coordinates, and from this scale, this is X scale, that is the germanium concentration, and this is the relaxation scale. So you can find both the things without any calculation. You can save a lot of time while industrial production. This is very important. Next slide please. Okay, this in the health sector, how Raman can be useful in the health sector. Actually, this is used to identification of the bacteria and the cancer diagnosis at a much earlier stage, and also Alzheimer's problems also can be detected by this Raman spectrometer. You see here, it is the cancer will not go immediately from the non-cancer state to the neoplastic cancer state. So in between there are two more states actually. So the Raman will give the signal, undoubtedly you are going to have a cancer. So that type of things, one can, early detection of cancer is possible by this Raman spectroscopy. Next is virus. You can also detect the virus. Actually so far RT-PCR, that is the reverse transcriptase polymerase chain reaction, is the only one reliable test to identify the virus, but it will take 3-4 days for the sample preparation and so on. It is a costly technique also, particularly when it is in the early stage. it will give the unacceptable false positive or false negative cases. In such a cases, Raman spectroscopy is very useful. In this actually, why the problem is, the basic problem is the mass of the virus is very, very, very small. Its size is in nanometer, you can understand. So, the signal, the output signal is naturally very, very, very less. So, therefore, there is a problem. But in the surface enhanced mode of Raman spectroscope, using carbon nanotubes and which are coated by gold or silver, you can detect with an accuracy of 10 to the power of times. The signal will increase 10 to the power of 11 times. Therefore, you can easily identify and quantify the virus that you are affected. Next slide, please. Okay, these are the applications of Raman spectroscopy in health sector. You can find the cancer or tumor at a very early stage, and you can identify the bacteria and other pathogenic microorganisms, and the structure of the drugs can be determined or identify various functional groups, and also you can know the composition of this cholesterol deposits in the arteries, that is also possible, and forensic studies and also the quality control. All these things can be done by this Raman spectroscopy. Next slide, please. Okay, next come to this recent interesting topic of quantum computing. It is a new concept of societal importance. Actually, it uses quantum mechanics to solve complex problems much faster, that is 10 to the power of 6 times than that of a classical computer, and going to be a big boost to the artificial intelligence. So this uses subatomic particles such as electrons, photons, trapped ions, and so on. And there are three fundamental concepts of quantum computing, that is qubits or quantum bits, superposition and entanglement. Let us see quickly what is these things. This traditional computer as well as this quantum computer, they have both these distinct states of 0 and 1. But what is the main difference? That is actually superposition of these two states is also possible. So this ability to simultaneously be in multiple states is called quantum superposition, and is responsible for the enhanced speed with simultaneous calculations, the so-called quantum parallelism. Actually, it is quantum mechanically, it is quite possible because the linear combination of solution is also a solution of the Schrödinger wave equation. So that way it is mathematically it is also true, and we are using the same concept in the quantum computing. And depending upon the architecture, actually qubit technology, there are 7 key technologies. It sometimes depends on the extreme cold conditions also, depending upon the technique that technology that we have used. Next slide, please. Next slide. Okay, so how you can really recognize or understand the superposition of light? You see, for example, the light around us is a superposition of so many light waves. So this actually, now we actually to realize this superposition, you better make it a horizontal polarizing light. In this, only horizontal polarizing light will pass, and if it is encountered a vertical polarizer, no light will pass from this vertical filter. But surprisingly, if you put this diagonal filter, though it is a bit obstruction also, but a light will pass on. Finally, we will get some light here. You see, when we are putting one more obstruction, of course, it has some this thing, that is a diagonal this thing, but you are getting some light actually. When you are putting one more thing here, this is because of the superposition. So this can also be understood by some more from this combination of a single and a double slit experiment. In this actually, there is, suppose when there is only one slit, let it come. So like this, one slit only, then at this point you have some light which is denoted by yellow light, but when you open the second slit, the interference pattern is changing, and this is a minimum light. So that means when we are opening another light source, so the earlier detected light is disappearing. So this is somewhat, it is surprising to think that way, but superposition it explains this thing. I think you understand this. Earlier with single slit, there is a light at one place, and when you open another slit, now that is disappearing. So this is also true with the electron and other subatomic particles. In this, so then Feynman asked, can that single particle know that two slits are open? Yes, logically the answer is yes. Though the particle is far from the slit, it behaves as if it knows that the second slit is open. Logically it is true. Next slide please. Okay, then quantum entanglement is another fundamental aspect of this thing. That is, it is originally postulated by John Bell in 1964. It is a phenomenon that explains how two subatomic particles can be intimately linked to each other, even if separated by billions of light years. Despite their vast separation, a change induced in one will affect the other. So a group of 3 scientists, Allied Aspect and others, they demonstrated this phenomenon successfully that led to earning the Nobel Prize combined. This they have demonstrated the quantum entanglement in space, but it is up to that it is a time domain of another team of physicists led by this Martin. He demonstrated that quantum entanglement is not limited to the space but also across the time. So they used some photon pairs, beryllium ion pairs, and Josephson phase qubits and so on. And this can be, in a very simple way, this can be used by nonlinear optical crystals. What I have shown a bit earlier in the beginning, the crystals that we have grown here. Actually, if you pass this laser beam through a nonlinear optical crystal, with the down conversion of photon, you will get two entangled photons which are having 90 degrees polarization. They are entangled actually. If there is a change in one, automatically the other photon also will have change. So this is how you can use these nonlinear optical crystals to get this entangled photon. And similarly, the quantum dots also, with the quantum dots, with the down conversion photon process, you can also get the entangled pair of photons. I will explain that also. Okay, this is a famous cartoon for the entanglement. Okay, so this is another important aspect of the research methodology to find solutions for our daily needs like energy harvesting, health security, and environmental protection. So there are many well-established renewable energy generators like ethanol from molasses, that is sugar factories. They get this molasses, from that ethanol can be made, and waterfalls, water streams, etc. You can make this microhydro electric power plants that does not require big dams, etc. And also we can extract the geothermal power, which is already found in Khammam district in Telangana. Like that, we have a variety of things, but today it will take another 1 or 2 hours of a lecture. But I will tell as a typical example. I will tell about this quantum dot solar cells only, and conservation of energy as well as generation of energy. We can use light emitting diodes to save the materials, can be used to save the transmission losses and so on. Next slide please. Okay, next nanotechnology. This is actually it is an upcoming new technology, and it is used for societal application. This is one more aspect of this technology. To get this can be used to get green energy harvesting through third generation solar cells. A typical example of a quantum dot solar cell, and the biomedical application for drug delivery, targeting and imaging, and we can have other things, and then environment protection and nanosensors is also can be used by this, can be developed by this nanotechnology. Next slide please. Next. Okay, wait. So first of all, I would like to, because it is a new concept, I would like to give a little introduction about the nanotechnology. Here, first of all, one should realize how small the nano is. Nanometer means 10 to the power of -9 meters, and it is actually one single wall carbon nanotube. 1 lakh times of its size will be equivalent to the diameter of a strand of a hive, and 1 lakh times is equivalent to the 10 meters that is width of a house. So you can see that how small this nano is. Next slide please. Next. Okay. Actually, when you go on divide the bulk material, the atoms on the surface will go on increase, and therefore the ratio of the atoms on the surface to the volume atoms will increase exponentially. So that means we have lot of atoms on the surface. Automatically, the surface energy, reactivity of the surface will go on increase exponentially. That we can tap for different applications. Next slide please. So this is actually when you are breaking a solid, so you have to do some work against or break the chemical bonds. That these are the non-coordinated broken chemical bonds, and these are towards the external volume of this sample. And here you see there are so many dangling bonds. So these are having high energy and high reactivity. You can add many interesting functional groups to have our work done. Next slide. Sorry. Okay. So because of that dangling bonds, you can attach many functional groups, like you can attach drugs, the antibodies and fluorescent dyes to image the diseased place or organ or a tissue. You can attach so many things for these nanoparticles, and you can use in the medical field. Next slide please. Okay, so I am not going to all the properties, but this electrical and optical only I am going to touch. Here, in the bulk material, you have a continuous conduction band and a valence band. They are continuous, but when their size is a nano region, that is 1 to 100 nanometer, then your not only the band gap increases, but there are discrete energy levels, just like in an isolated atom. So because of this, quantum tunneling will take place, and the same material, when we size for different sizes, they act as if they are different materials from one another. So you see this is the same material, cadmium sulfide colloidal particles here, and they are showing different colors. And similarly, your board also, if you make it nano, you can see all colors in any material. So that is the thing. And okay, next slide please. Okay, these are actually quantum dots. We have. Please go back. Please go back. Okay. So I am talking about the quantum dots many times. So let us see how we can make this actually. When you make a film below a critical thickness, we will get a good film. But when the thickness is gone increasing, to release the strain, the plane takes the undulation, and finally you will get a dot here. They are actually crystallographic. They have the crystallographic phases. These are actually self-assembled quantum dots. So you can see in a very orderly way, you can make nanoparticles on a suitable substrate. These are called quantum dots. We have a lot of applications with this. Next slide please. So this is actually, you can, if a photon is incident on a quantum dot, it is a photosensitive material, and it will absorb and it will release an electron hole pair. But here, because of the high energy of this incident photon, the excess energy of the electron will lead to one more pair of the electron hole. So therefore, for one photon, you are getting more than one electron hole pair. So this is what we need actually to improve enhance the efficiency of the solar cell. So this is what actually. Suppose if you excite this quantum dot having this discrete energy level by some high energy electron, you will get a quantum two photons which are having quantum entanglement, so which are needed for the quantum computing. So that way also these are useful for the quantum computing. Okay, next how we can construct this. Actually earlier we used to use the costly molecular beam epitaxy for the quantum dots. But now it is not necessary of using such a costly techniques. You can use this wet chemistry. You make a colloidal solution, concentrated colloidal solution, in which the colloidal particles are actually the nanoparticles. They are nanocrystals rather, and these are very stable in the solution, and with their long hydrocarbon ligands, that the solution is very stable. Now, using this concentrated colloidal solution, you make a deposit on a spinning substrate, and you can get a uniform film. And after casting it, you will get this long hydrocarbon ligands become the strong cross linkers, and the layers will be converted into quantum dots, which are useful for the absorption of the light in a solar cell. So here you can actually, instead of using multi-junction solar cell, you can use the multi-layers of this quantum dots in a tandem way. You can absorb all wavelengths in the solar spectrum. Otherwise, it is going to be waste. Suppose there is a silicon illumination solar cell. In that, 1/3 of the near infrared energy is only used, though it is the highest, it is having the highest efficiency. So, but with this, you can increase the efficiency of the solar cell, and you have here one transparent electrode is there, but it has a ohmic this thing, conduct electrons, and N junction, P junction, and anti-reflection coatings, and then ohmic contacts are there. So next slide please. So this is how it works actually. With this transparent electrode, the photons are going to the quantum dot, and their electron holes pair are creating, and this electron holes in this TiO2 mesoporous semiconductor, it simply, its bandwidth is very high, so therefore it won't absorb, it simply percolates and reaches the collecting electrode, and the electrons will go through the load where it will deliver the power, and then it come back through the counter electrode, and it will replenish the electrons, and it is ready for the next cycle. Next slide please. So you can assess these solar cells, and by IV characteristics, it can be defined by this equation, and then one more fill factor. And of course, to improve the efficiency, we have to do surface interface passivation and use of core shell to give the stable solar cell. Next slide please. So this is about the advanced biomedical application for drug delivery, targeting and imaging, including treatment of viral diseases. Actually, this, as you have seen, this nanoparticles, because of